finding the domain, the principal domain for inverse trig functions. If you have a look at the graph over here, it is the graph of sine theta. How do we know that sine theta itself is a function? If we take a vertical line and we move the vertical line anywhere over this graph, you will see that this vertical line that I'm moving over the graph cuts the trig function in one place only, meaning that this sine function, this trigonometrical function, that this trigonometrical graph is a function. This is why we refer to the trig graphs as the 6 trigonometrical functions. They all obey the vertical line test. A vertical line will cut all of these graphs in one place only. Now, in order to see if its inverse is a function, the graph needs to obey the horizontal line test. That means a horizontal line has to cut it in one place only in order for the inverse of the function to also be a function. Now, if I take this red horizontal graph and I move it over my sine graph, you can see that it is cutting it in 1, 2, 3, 4 places. And it's cutting it in 4 places only because the domain is from negative 2 pi to 2 pi. Remember that the sine theta function really carries on from negative infinity to positive infinity. So a horizontal line would actually cut it in an infinite number of places. This means that the inverse of the sine function is not a function. What we would like to do over here is to restrict the domain of y equals sine theta so that the sine function, that the inverse of the sine function is also function over that restricted domain. I have now restricted the domain. Instead of from negative 2 pi to 2 pi, I have restricted the domain from negative pi to pi. Let's see now if this horizontal line will cut the sine function in one place only. No, it is cutting it in 2 places. That means with this domain, the inverse will still not be a function. I want to find a way of restricting the domain so that it will cut it in one place only. Here I'm moving the line. You can see if I start off at 0, restricting the domain, it is now going to cut it in one place only. Moving it along, you can see as soon as we go beyond pi over 2, this is where the problem is. So if I had to move this horizontal line a bit further up, you can see the problem comes as I move over pi over 2. As I move over pi over 2, it is going to cut it in more than one place. I have now restricted the domain of the sine graph to be from negative pi over 2 to pi over 2. Have a look when I take the horizontal line. You will see now that it will cut the graph in one place only. As I move it along, it cuts it in one place only. If, however, I had to extend the graph beyond pi over 2, it would cut it again in 2 places. If I had to extend the graph beyond negative pi over 2, it would again cut it in 2 places. So the principal domain, it is called the principal domain for the sine graph, principal domain for the sine graph is negative pi over 2 to positive pi over 2. Restricting the graph to that ensures that the inverse of the sine graph, that is the angle, the arc sine, the angle, will be a function. The same with the cosine graph. We can see that y equals cosine theta is a function. It would obey the vertical line test. But when we take a horizontal line, the same as with the sine graph, we can see that a horizontal line will cut it in more than one place. Thus, the inverse of the cosine graph is not a function. Restricting this graph, as we did in the sine graph, from negative pi to pi will definitely not help, because as soon as we go to the left side of 0 radians, it immediately disobeys the horizontal line test. That means a horizontal line will cut it in more than one place. And if that happens, the inverse of the cosine is not a function. So in my next window, in my next picture, I'm going to restrict it from 0 to 2 pi and see if we can find a domain for the cosine in which the inverse will be a function. Taking the horizontal line, which I have over here, you can see that if we start at a 0, the inverse is a function. All the way moving it down, it would be a function until I reach pi. As soon as I go over pi radians, the inverse is not a function. So in order to get the principal domain, the domain over the cosine, that the inverse will be a function, it needs to obey the horizontal line test. Thus, I will have to stop my graph at pi radians. So, taking my horizontal line, I have now restricted the domain to between 0 and pi, and when I move the horizontal line over my graph, you will see that it cuts it in one place only. If I would go beyond pi, it would be in two places. So we need to restrict the domain to be between 0 and pi. Now it obeys the horizontal line test, so making the principal domain for the cosine function to be between 0 and pi. Drawn in red is the graph of y equals tangent theta. It's also functioned as a vertical line would cut it in one place only. The dotted lines are the asymptotes. The tangent graph gets close and closer to them, never ever reaches them. You can see that the inverse of the tan function is not a function, because a horizontal line, which I'm drawing over here, will cut it in more than one place. Again, we need to restrict the domain of the tangent to get the principal domain so that the inverse will be a function. Restricting the domain of the tangent to negative pi over 2 to pi over 2, you will see that a horizontal line cuts this graph in one place only. I could move the horizontal line anywhere over this graph and it would cut it in one place only, making the principal domain for the tangent graph to be from negative pi over 2 to pi over 2.